Welcome to E-Pathshala lecture series in computer science. This course is on operating systems and today we will learn about CPU scheduling. So, the objectives of today's lecture will be to learn about the basic concepts of CPU scheduling, to know different criteria using which CPU scheduling algorithms are being evaluated, to understand the working of different CPU scheduling algorithms. So, first we will look at the basic concepts to understand different CPU scheduling algorithms. We have already learned that multiprogramming helps to have a number of programs in the machine, the memory at the same time. And because of this, when one program finishes using the CPU, the next program will be immediately given the CPU. And hence because of that, the CPU will be utilized continuously and hence the CPU utilization becomes maximum. So, multiprogramming favors CPU utilization. And now when you are looking at any program that runs in the CPU, it will have a number of CPU related instructions as well as IO related instructions. So, if you look at any program, it will not be having only CPU instructions or only IO instructions. There will be a mix of both CPU and IO instructions. So, if there is a sequence of instructions that needs to use a CPU, that is called a CPU burst. And if there is a sequence of instructions that need to use only IO, then that is called an IO burst. So, when you look at any program, you will have a sequence of CPU burst or you will have a sequence of CPU instructions, then IO instructions, CPU instructions and so on, or there will be alternate CPU bursts and IO bursts in the program. So, when you are looking at this example, see here you see that there are a few instructions, say load, then add and then read from a file. So, when you want to read from a file, you have to do IO. So, before that there are a few instructions like load and add which are CPU bound instructions, and then the process goes to wait for IO till it reads from the file. And then after reading from the file, then again comes back, it needs to store something, then index, and then again there is an instruction to write to a file. So, the first two here, the store and index are CPU related instructions, and then this write is writing to a file which is again an IO instruction. So, the process again goes to wait for IO. So, now there is an IO burst. Then again you have load, add which are CPU instructions, and then read from a file which is an IO instruction and so on. So, you have a number of CPU related instructions and then IO, then CPU and so on. So, this is how any program will be. It will have alternating sequence of CPU and IO bursts. And when this CPU burst times and IO burst times were analyzed, they found that, researchers found that, see the burst during the x-axis, here you have the burst duration in milliseconds and here the frequency of these occurrence. So, it is found that this short CPU burst was occurring more number of times and long CPU bursts were occurring only few or less number of times. The frequency of occurrence of short CPU bursts is more rather than long CPU bursts. So, which means that there will be short CPU burst and naturally the process goes for IO and then again comes back, there will be again short CPU burst and so on. So, this helps in analyzing and designing CPU scheduling algorithms. So, when a program has got few and very long CPU bursts, that is called a CPU bound program. So, in the CPU bound program, there will be only few CPU bursts, but the CPU bursts will be very long. And if in a program there are many very short CPU bursts, then that is called a IO bound program, because most time or a lot of times the program will be waiting for IO. So, now we will learn about, having seen the basics, we learn about what CPU scheduling is and what a CPU scheduler is. The CPU scheduler is also called a short-term scheduler. What does it do? There are a number of programs that will be waiting in the memory, in the ready queue and waiting to get executed. And the CPU scheduler is the one who is responsible to pick out one process from the different processes or for the number of processes that are waiting and assign that process to the CPU. So, we have already learned that a process can be in a ready state, waiting state, etc. and so on. So, all processes that are waiting to execute will be present in the ready queue. So, the CPU scheduler is responsible to select one among these processes and give to the CPU. And this ready queue can either be a first in first out queue, it can be a priority queue, it can be a tree, any kind of data structure can be used to implement this ready queue. So, now we will see here that, when CPU scheduling takes place, so there are a number of instances when a CPU scheduler can run. Say for example, you look at this diagram, there is a process in the running state, there is a process, there can be processes in the ready state, there can be processes in the terminated, new, waiting and so on. Whenever a process is running and if an interrupt happens, then this process has to go back to the ready state and wait for the interrupt to be serviced. In the meantime, another process can be picked up and be given the CPU. So, then at that time the CPU scheduler will run. And say a process is currently running and the process gets terminated. And now the CPU is not being used by anyone and again the CPU scheduler will run to pick up one of these processes. And then it is also possible that running process can go to a waiting state, which means that again the CPU is free, is not being used and another process is picked up and is given the CPU. So, here you find that in certain instances the process is by itself relinquishing the CPU. Say for example, when a process goes from running to terminated state, then the process is relinquishing the CPU by itself or leaving the CPU by itself. No one is forcing the process to remove, forcing the process to relinquish the CPU. And also when a process is going to the waiting state also, the process by itself leaves the CPU. But when there is an interrupt, there is someone who is forcing the CPU process to come out of the running state. And also suppose if the time slice gets over, say a process is given a particular amount of time to execute and if the time slice gets over, then in that case the process is forcibly removed from the CPU. And so there are certain instances when the process is forcibly removed from the CPU and certain instances when the process by itself relinquishes the CPU. So, whenever a process is forcibly removed the CPU, then it is called a preemptive kind of scheduling algorithm. And when the process by itself relinquishes the CPU without any force, it is called a non-preemptive scheduling algorithms. So, in this course we will learn about a number of scheduling algorithms and we will see the features of each of those scheduling algorithms. And in addition to scheduling algorithms and in addition to schedulers, you have another component of the operating system which is called a dispatcher. So, what is the difference between a scheduler and a dispatcher? The scheduler is responsible for selecting one among the many processes that are waiting to get the CPU. This dispatcher does the next work, that is, it gives control of the CPU to the process which is actually selected by the short-term scheduler. So, this involves switching context, that is, what is switching context? The context of the old process should be saved and the context of the newly selected process should be loaded. So, now the CPU scheduler has selected a new process and the dispatcher is supposed to load the new process into memory and to start it executing. So, the control should go in the new process, the control should go to the user mode, and then it should jump to a proper location in the user program so that the program can be started. If the program had executed earlier halfway through, and again if it is getting the CPU, then it should know the point from where the program should get restarted again. So, this takes some amount of time. That is, after the CPU scheduler had selected which process should be given the CPU, this dispatcher takes some amount of time to switch the context, to switch the process to the user mode, to find out the location from which it has to start executing, and so on. So, this amount of time is called the dispatch latency. That is the time that taken by the dispatcher to stop one process and to start the next process. So, when different CPU scheduling algorithms are being designed, there are a number of criteria based on which you can evaluate a CPU scheduling algorithm. So, first is CPU utilization. Any CPU scheduling algorithm should be designed such that the CPU utilization is a maximum. That is, the CPU should be kept as busy as possible. The CPU should not be kept idle. And the next is throughput. That is, the number of processes that complete their execution per unit of time. That should be high. So, the throughput should be maximized. Then you have turnaround time. What is turnaround time? The time in which a process is taken for execution till the time in which the process completes execution, that is turnaround time, or it is the amount of time that is required to execute a particular process. And this turnaround time should be less, or process should get completed as early as possible. Then you have the waiting time. Waiting time is the amount of time a process will wait in the ready queue, and this time again should be reduced. Then you have response time. Once a process is taken for execution, then if a user places a request as a part of that process, how quickly will the user get the first response? It is not actually the final output that the user gets, it is the first response that the user gets. So, the response that the user gets should be as quick as possible. So, having all these criteria, what should be the optimization criteria is that we need to maximize the CPU utilization, we need to maximize the throughput, we need to minimize the turnaround time, minimize the waiting time, and minimize the response time. So, with all these criteria in mind, different algorithms have been designed, and we will see the CPU scheduling algorithms, the working of them one after the other. So, the first algorithm that we are going to see here is this first come first served scheduling algorithm. And in this algorithm, we are considering three processes P1, P2 and P3, and each of these processes have corresponding burst times. This P1 can make use of the CPU continuously for 24 milliseconds say, or the burst time is 24 time units, and for P2 it is 3 time units, and for P3 it is 3 time units. And it is assumed that all the processes arrive at the same time, but there is an order in which they arrive. The order is P1, P2 and P3. Now, we will see how this first come first serve scheduling algorithm will schedule these processes. So, just as the name says, we can understand that it schedules processes based on the order in which they arrive. So, whoever comes first will be served first. So, here the order is P1, P2 and P3. So, the first process that arrives is process P1. So, P1 should be scheduled first. So, we find that here we see that P1 is scheduled. So, this chart is actually called a Gantt chart, which shows the time at which each process is being scheduled. So, process P1 is scheduled first and its burst time is 24 milliseconds. So, it will make use of the CPU or keep the CPU for 24 milliseconds. It will not relinquish the CPU by itself. In the case of first come first served, you need to see that it does not relinquish the CPU by itself. and no one will forcibly remove a process from the CPU also. It is a non-preemptive scheduling algorithm. So, once a process gets the CPU, it will hold the CPU till it finishes off the burst time. So, the first process is being assigned the CPU and it makes use for 24 milliseconds. Then you have the next process. Which one arrives next? It is process P2. So, P2 is given the CPU next. So, and P2 will be using the CPU for the next 3 milliseconds and hence the time now is 27 milliseconds. And the next one to be scheduled is process P3. So, P3 has arrived next. So, P3 is given the CPU next. So, now we have P3 being using the CPU for 3 milliseconds and hence we have 30 milliseconds totally. So, we see that P1 is scheduled first, next P2 and P3 because they arrive in the order P1, P2 and P3. So, the total time taken now is 30 milliseconds. Now, with this Gantt chart, we can calculate two parameters. One is the average waiting time for all the processes and the next is the average turnaround time for all the processes. So, how is this waiting time calculated? For process P1, it came in or arrived at time t0, t equal to 0 and it made use of the CPU till 24 and it finished its work at t equal to 24. And hence, the waiting time for P1 is 0 and the turnaround time for P1 is 24. Okay. And for process P2, the waiting time is 24 and the turnaround time is 27. And for process P3, the waiting time is 27 and the turnaround time is 30. So, now when we calculate the average waiting time, for P1 it's 0, for P2 it's 24, for P3 it's 27 and hence it is 0 plus 24 plus 27 by 3, it's 17. And we are looking at turnaround time. For P1 it is 24, for P2 it's 27, for P3 it's 30 and hence the average turnaround time is 24 plus 27 plus 30 by 3, that's equal to 27. So, this is how this scheduling has been working. Now, here we see that this P1 is a very long process and because this P1 was scheduled first, it was found that P2 and P3 had to wait for a long amount of time. So, suppose if the process had arrived in this order, suppose if process P2 had arrived first and then P3 had arrived and then say P1 had arrived, then how will the Gantt chart for the schedule look like? Because P2 had arrived first, you have P2 being scheduled first and then P3 being scheduled and then finally P1 being scheduled. So, P2 will make use of the CPU for 3 milliseconds, P3 will use for 3 milliseconds, totally 6 and then P1 will use for 24 milliseconds and hence totally 30. Now, how will the waiting time and turnaround time be? The waiting time for P1 is 6 milliseconds, for P2 it is 0, for P3 it is 3 and hence the average waiting time comes down to 3. The average turnaround time comes to 3 plus 6 plus 30 by 3, that is 13. For P2 the turnaround time is 3, for P3 it is 6 and for P1 it is 30 and hence it becomes 13. The average turnaround time becomes 13. So, here we find that the average turnaround time gets reduced than the previous. In the previous, here we see that the turnaround time, average turnaround time is 27 and the average waiting time is 17. But now, the average waiting time has become 3 and the average turnaround time has become 13. And hence, we see that this is much better compared to the previous case. Why does this happen? Because, see, when you have a long process which goes in first and there are short processes that go after the long process, that results in something called a convoy effect. What is this convoy effect? It is like, say you have one CPU bound process and a number of IO bound processes. So, the CPU bound process, one long CPU bound process will be making use of the CPU for a very long amount of time. And then the IO bound process will come into picture. The IO bound process will be waiting till the CPU bound process finishes off the CPU. And it would have finished the IO because CPU bound process is taking a long amount of time. The IO bound process will be waiting for the CPU bound process to finish off. And when the CPU bound process finishes off and goes for IO, these IO bound processes, all these need only short CPU burst times. So they will finish off their CPU execution, they will also go wait for IO. Now the CPU remains idle. And when the CPU bound process again comes back for CPU execution, the IO bound process will finish off IO and come back, and again IO devices will not be utilized. So here we find that there is a convoy effect, that is one long process making other short processes to wait behind them. So this is one effect that is prevalent in first come first served scheduling algorithm. And based on the two examples that we have seen, we saw that in the second case, we saw that this P2 and P3, they were short processes, short jobs. If they were executed earlier, then the average waiting time and average turnaround time becomes less. So what do we understand out of this? If the average turnaround time, if the short processes are being executed first, then you get a better performance in the CPU scheduling. So they came up with this scheduling algorithm called the shortest job first scheduling algorithm. So in this scheduling algorithm, what is done? Whichever process has got the shortest burst time is given the CPU the next time. So with each process, you assign a length of the next CPU burst, and these lengths are used to schedule the process. And this shortest job first scheduling algorithm has got two cases, non-preemptive and preemptive. When we saw FCFS, we saw that FCFS is non-preemptive. No one forcibly removes the process from the CPU. But here both options are available. It can either run as a non-preemptive algorithm, or you also have a preemptive algorithm. So in non-preemptive case, once the CPU is given a process, it is not preempted at least until it completes its CPU burst. And in the case of preemptive algorithm, if a new process arrives with a short burst length than the currently running process, and if the short burst of the new process is less than what more the current process can or has to run, then the current process is preempted and the newly arrived process is given the CPU. And this scheme is also known as shortest remaining time first algorithm. So we will see how this short SJF works, and we have found that this SJF, we will see that this SJF is an optimal algorithm. It will give the minimum average waiting time, but the problem here only will be that how will we know what length will be the next CPU burst? We won't know. We only know the order of the processes that arrive. We won't know how much time or how much CPU time the next process will take, or if there are many processes that are waiting, we won't know how much amount of time should be given for each of the process or will be needed by each of the process. That will be the practical difficulty. So we will now see this example of non-preemptive SJF. So in this non-preemptive SJF, we look at different processes P1, P2, P3 and P4, and the arrival time of the processes are given. They arrive at different times, they do not arrive at the same time, and the burst times is also given. And now how will this work when it is non-preemptive? As I told you earlier, in non-preemptive, once a process gets the CPU, it will use the CPU and it will not be forcibly removed from the CPU. So first process at time t equal to 0, only one process is present, because P2 comes only at 2, P3 comes at 4 and P4 comes only at 5. At t equal to 0, P1 is present. So P1 is given the CPU. Even though at t equal to 2, P1 would have completed 2 units of execution here and remaining will be 5. But P2 arrives with needs only 4 more to finish off. But still it is not preempted because it is a non-preemptive algorithm. So once it gets the CPU, P1 will use the CPU till t equal to 7, finish off its burst. When t equal to 7, now all the 3 would have arrived, because at 5 itself P4 arrives. So P2, P3 and P4 have arrived at would have arrived at t equal to 7. So now next who will be scheduled? we have 3 processes and the burst time of P2 is 4, the burst time of P3 is 1 and the burst time of P4 is 4. So, for all these, of all the 3, the shortest is P3. So, P3 is scheduled next. P3 is scheduled next and P3 will run for 1 millisecond, finish off its CPU burst. And then we have P2 and P4. Of P2 and P4, which will be scheduled next can either be P2 or P4 because both have the same time burst time. So, P2 or P4 can be scheduled, or you can break the tie using FCFS. Because P2 had arrived earlier, we can give the CPU for P2. And then you have P4, P4 is scheduled next. So, now we need to calculate the average waiting time and the average turnaround time for the process. Here we need to consider the arrival time also. So, if you are looking at waiting time, P1 arrived at t equal to 0, it got scheduled at t equal to 0, so the waiting time is 0. But P2, it arrived at t equal to 2, but got scheduled only at t equal to 8. So, the waiting time is 8 minus 2. For P3, it arrived at t equal to 7 and the waiting time is arrived at t equal to 4 and got scheduled at t equal to 7. So, waiting time is 7 minus 4. Similarly, for P4, so the average waiting time is this, it is 4. And if you look at turnaround time again, you need to consider the arrival time. So, process P1 finishes off at 7, it arrived at 0. So, the average turnaround time for process P1 is 7 minus 0. For P2, it is 12 is turnaround, it finishes at 12, it arrived at 2, so it is 12 minus 2. P3 finishes at 8, it arrived at 4, the turnaround time is 4. And P4 finishes at 16, it arrived at 5 and turnaround time is 16 minus 5. And so, we have the average turnaround time like this. So, we will conclude today's class. We will have this look at the summary of what we had seen today. So, we saw that multiprogramming maximizes CPU utilization because once one process is being taken off from the CPU, the next process is given the CPU. And then we learnt about CPU scheduling. CPU scheduler is one which will select which process among the ready process should be given the CPU. And many CPU scheduling algorithms have been proposed, and we saw FCFS algorithm and SJF algorithm, and the CPU scheduling algorithms can be either preemptive or non-preemptive, and FCFS algorithm is the one which will assign to the CPU whichever process comes in first, and this FCFS is non-preemptive, but it has got a convoy effect problem. And SJF will assign the shortest job to the CPU, and today we learnt about non-preemptive category of SJF algorithm. But SJF can be either preemptive or non-preemptive. So, the references, acknowledgement, thank you.